Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. This is Professor Mahendrakumar Madhavan, Professor, Department of Civil Engineering at IIT Hyderabad. I lead the Structural Steel Research Group. The website shown at the right hand side gives you more information about my research activities. The objective of this course is to enable the audience to understand the core philosophy behind the development of design provisions available in IS 800-2007, which can be directly traced back to the fundamental understanding of structural stability. Stability of structures and structural steel design are often considered as two different domains. However, a profound understanding of stability of structures is necessary to properly design the steel structures. This course seeks to bridge the gap between these two domains by formulating stability equations based on fundamental principles. The course structure will ensure that students gain a profound understanding of the origin of design provisions. This will enable them to comfortably apply the concepts learned to design safe and stable steel structures with an inherent understanding of the limitations and their applicability. Upon completing this course, students are expected to confidently navigate global steel design standards. The emphasis of the course on tracing these standards back to fundamental principles in structural stability will significantly enhance the understanding of the students, equipping them to be industry ready on a global scale. The duration of the course is for 12 weeks and it has been divided into segments. Segments 1 to 4 basically cover the columns, 5 to 8 cover the beams, and 9 to 12 cover the plates. So let's look into columns. In this column chapter, we'll begin with the importance of stability. What happens when you do not consider stability? It results in catastrophic and sudden failure. There are several failures in history due to stability issues. And the one that you see on the left hand side is the Tacoma Narrows Bridge, which collapsed in 1940. And the one on the right hand side is the Ronan Point collapse, which happened in UK in 1968. We will also talk about the design equations and structural steel design codes, and you can also see that all these equations that are there here actually have their origin in stability. We will talk about that. We will also talk about states of equilibrium and why that needs to be taken into consideration. What are the three states of equilibrium? How we can determine that using what is known as a perturbation technique. The first one that you see is a stable equilibrium. The next one is the unstable equilibrium condition. And the third one is the neutral equilibrium conditions. We will also talk about the concept of buckling, how a sudden change in geometry of a structure under compression results in its inability to resist loads, which we term it as buckling. The one on the left hand side is the state 1, on the right hand side is the state 2. In state 1, the load applied is less than the critical load for axial compression. So, there is not much change in geometry, but when it crosses the P critical, then there is a sudden change in deformation. Basically, you apply the load in the axial direction. The deformation is perpendicular to the application of the loads, and this is defined as buckling. There are several types of buckling. We will talk about bifurcation buckling, where there is a bifurcation point, there is a sudden change once it reaches P critical. There is also known as limit point buckling. As you can see, that limit point buckling is basically due to the imperfections that are present in the structure. It starts with delta naught, as you can see from the x axis in the right hand side. So, delta naught represents the initial crookedness of the column. We will also talk about snap through buckling, where it goes from point A to point B suddenly, and this phenomenon is called snap through buckling. You can experience snap through buckling using a Coke can. When you press a Coke can, you will see that there is a sudden change in geometry, which typically is an example of a snap through buckling. We can also talk about finite disturbance buckling, how the imperfections actually decrease the load carrying capacity, how a geometrically perfect shell has very high load carrying capacity, it reaches N critical, as you can see here, and an imperfect shell, there is load carrying capacity is much lower. And we will also talk about the concepts of buckling using spring bar models. It is an illustration of buckling. Spring bar models are an easy way to understand buckling because spring bar models do not undergo deformations. The objective of understanding a spring bar model is simply to ensure that you do not have to dwell with lots of complicated differential equations. Rather, you can use algebraic equations to understand the concept of buckling without getting clouded into mathematics. So, we will talk about large deflection theory, small deflection theory, and then how it leads to equation of equilibrium path and equation of limit state of stability. Then we'll talk about Euler columns. How an understanding of Euler columns is extremely important for us. Euler columns are ideal columns, which means that they are geometrically perfectly straight, and we'll also talk about the critical load for ideal boundary conditions. The one you see is the pin-ended column, and the next one is a fixed-ended column. The third one is a fixed free column, and then the fourth one is the fixed and pinned column. And these are all ideal boundary conditions, but in reality, most of the structures do not exhibit perfect simply supported condition or perfect fixity. We need to understand that practical columns do not follow ideal boundary conditions. So we need to understand solving critical load for practical boundary conditions, which can be employed by using what is known as a matrix method. So we will talk about the connection between beam and a column, or we will also talk about structures whose boundary conditions are not ideal. Here the boundary conditions are represented by means of both a linear spring as well as rotational spring, and the spring stiffness will determine the amount of fixity. From here we will talk about inelastic buckling theories. Inelastic buckling theories are important to understand the failure of a stocky as well as short columns. We will talk about double modulus theory, we will talk about tangent modulus theory, and we will also talk about chainless theory. And the picture here shows that the chainless theory is in between tangent modulus theory and reduced or double modulus theory. These derivations will be done in the course to give you a better understanding of the importance of failure theories of columns. We will also talk about imperfect columns. Imperfect columns are basically practical columns with imperfections. So there are two types of imperfections. One is a geometric imperfection, which is at a member level. We will talk about crooked columns, basically columns which has initial eccentricity or initially deformed shape. We will also talk about eccentrically loaded columns, where the load is not directly applied at the centroid, but it is applied at an eccentric distance e from the centroid of the cross section. We will also talk about material imperfections at a cross section level. This actually boils down to residual stress. What are residual stresses? Basically uneven heating and cooling during manufacturing process. These are the typical residual stress pattern that we experience here. So you can see that 30% of the yield stress is actually the residual stresses. So these are all self-equilibrating stresses. So the compression force due to residual stresses should be equal to the tensile force. The web fan junction typically experiences a tensile force, as you can see from here. So this is the famous CTC pattern that we typically understand for I sections. And then you can also see that at the web it is TCT pattern. And this stress versus strain plot gives you the importance of residual stresses, how the residual stresses alters your load carrying capacity. There is a slight deviation, as you can see here. Once it reaches the sigma sub p, which is the proportional load, it deviates and it does not reach the perfect yield, but nevertheless it attains the load carrying capacity, as you can see here, that sigma p is the proportional load, sigma y is the yield load. So the difference between sigma y and sigma p is the residual stresses, which is denoted as sigma sub r. This residual stresses can be up to 30% of your yield stress. Now we will also talk about column design curves, the approach that are adopted by different countries. We will talk about European multiple column curves, which is based on Perry-Robertson formula. The one on the left hand side is basically the column curve, which has 5 different column curves, A0, A, B, C and D. IS 800 uses a similar type of column design curve, which you can see on the right hand side, but instead of A0 to D, we have A, B, C, D on the right hand side. Basically, it was influenced. I would say that IS 800 was heavily influenced by the column design curves present in European code. Why these column curves are in this fashion and how they originated. We will also talk about the American column design approach. We will understand the column design method in AISC 360. You can see that number of equations are given. We will derive these equations and make you understand how these equations came into picture. The why and how will be answered in the course. After which we will move to weeks 5 to 8, which is basically beams. We will talk about types of beams. Typically there are two types of beams. One is called laterally supported beams and another is called laterally unsupported beams. The laterally supported beams, as you can see from the picture, are laterally supported at the compression flange, and it undergoes only one type of movement, which is vertical in nature. It can be solved using mechanics of solids, whereas laterally unsupported beams actually not only go vertical displacement, but it also moves laterally in the u direction, and it will also twist, which is measured by gamma. So the beam undergoes 3 different deformations, u, v and gamma, and this laterally unsupported beams are governed by stability. whereas the laterally supported beams are governed by strength. So it is imperative to understand the stability of a member under twist, which means that we need to understand the effect of torsion. So which leads us to the outline of the course. Basically, we will start with torsion, and there are different types of torsion. We will talk about uniform torsion, also known as synchronous torsion, where only twisting will happen, and the solution for this is given by the mechanics of solids approach, which is T equal to Gj theta. And then next one is called the non-uniform torsion or the Vlasov torsion, where in addition to twisting, the member will also undergo what is known as warping. Warping is nothing but axial deformation that takes place, so the plane sections do not remain plane. So the solution for the torsional moment is given as T equal to Gj theta minus EIW into d square theta by dz square. Following torsion, we will also talk about elastic critical moment MCR. So this is a simply supported beam, as you can see here, and there are several different types of cross section that we typically deal with. One is an I section, which is an open cross section, and then there is a box section, which is a closed cross section. So basically we apply equal moment on both sides, the external moment of value m0, and the derivation for which will lead to the annexure E, basically that is given in IS 800. And so we will talk about the derivations and how this MCR value is what is given in annexure E, page 128 of IS 800. And then we will also talk about MCR for different loading conditions. In practice, beams vary from basic case. There are different types of loading acting. So we have unequal end moments M and NB acting, resulting in a single curvature, which is a Smiley curve, or you have M and MB, which can lead to double curvature. We can also have concentrated load. We can also have uniformly distributed load. Now the loading condition could be that the load is applied exactly at the shear center, as it is denoted in the right hand side of the picture. This is basically the theoretical or normal condition as per IS 800. We also have destabilizing or practical condition, where almost all the loads are applied typically in practice at the top flange. So it is not applied at the shear center, it is applied at the top of the flange, which is called destabilizing condition. The stabilizing condition is where the load is applied at the bottom, which tends to stabilize the structure. I will also talk about MCR for different support conditions. Different support conditions are basically lateral bending, twist and warping. So we can see the plan view here. So you can see that in the plan view, we can see that lateral bending is prevented, twisting is prevented, but warping is allowed, which means that the structure can deform in the axial direction. The next is basically the support condition that we see here. This is the plan view. Basically the plan view shows you the flanges and how the flanges are restrained. Here the lateral bending is allowed, twisting is not allowed, and warping is also not allowed, because this appears to be a fixed condition where it is welded to a steel plate, so warping is not allowed. The next condition is what you see here. You can see the third condition in the plan view. Lateral bending is not allowed, twisting is not allowed, as well as warping is not allowed. So this is what is known as a fully fixed condition. Next we will talk about effective length L sub LT against lateral torsional buckling. Table 15 of IS 800 gives you the effective length for simply supported beams L sub LT, and there are two types of restraints. One is a torsional restraint, another is a warping restraint. We will talk about torsional restraint and warping restraint. We will also talk about loading condition, which is normal, as well as destabilizing. This is given in page number 58 of IS 800 2007. So what is L sub LT in IS 800 represents? We will talk more about that. Now we will also try to come up with a generic equation for MCR. So generic equation is a function of different types of loading conditions, different types of support conditions, different types of cross sections. How IS 800 2007 account for in the generic form of MCR. So we also have different types of cross sections. Many of the cross sections that you see here, the shear center and the centroid do not coincide. The red color C is the centroid and the green color S is the shear center. So based on the difference between the shear center and the centroid, in the cross sections can be classified as singly symmetric cross sections or point symmetric cross sections. The crux of this is the eccentricity between the shear center and the centroid amplifies the actual U, V and gamma, which means that the larger the difference between the shear center and the centroid, more is the displacement in U, which is lateral, V vertical, as well as gamma, which is twist. We will also do some problems, and then we wind up basically beams. So we have completed 8 weeks now. Now we will move into the 9 to 12 weeks, which is to begin with plates. right? So plates, we'll talk about stability of plates, we'll talk about how plates are different from columns. You know, what you see on the left hand side is the bifurcation buckling of a column as well as the actual columns with initial imperfections. You can see the fundamental path as well as the secondary path, and you can see on the right hand side the plate where you can see that it is actually more than 1.0, which is the secondary path. The actual paths are given here in the dotted line, which is due to imperfections. So the load carrying capacity of plates is basically not limited to its critical load. Following the stability of the plates, we'll talk about critical load of plate buckling, which is indicated as sigma sub CR. Sigma sub CR is given as K into pi square E divided by 12 into 1 minus nu square into B by T the whole square, where K is the buckling coefficient, also known as the elastic buckling coefficient, which depends upon a variety of factors. It depends upon the support conditions, depends upon the loading conditions, it also depends upon the aspect ratio of the plate. Sigma y is the yield stress, sigma u is the ultimate stress of the plate, E is the Young's modulus, nu is the Poisson's ratio, T is the thickness of the plate element, and B is the width or breadth of the element. So we will solve this plate buckling equations using several approaches. We will discuss two approaches in this class. The first one is the differential equation method, where we use one common plate buckling equations. The next one is the strain energy method, where it takes into account the total potential energy of the system, and that includes the strain energy due to bending, which can be seen from the equation on the right side. We will also talk about the potential energy due to external loads V. The equation is also given here. Now we will talk about the critical elastic buckling stress for different loading conditions. We will talk about simply supported condition where it is uniaxial compression. We will also have biaxial compression here, or we can also have shear loading, as you can see here. Now we will talk about the post critical buckling of thin plates. The ability of a thin plate is to take more load or to undergo more deformation, more load beyond the critical buckling load. So we will talk about the post buckling reserve capacity and how the post buckling reserve capacity is a function of the thickness of the plate. So thicker plates have lesser post buckling and thinner plates have more post buckling, as you can see from here. Then we will talk about the design methods for shear buckling. There are two design methods that are available in IS 800. One is the simple post critical method and another is the tension field method. The simple post critical method is given by this equations, as you can see here. Plot is also given here. So after simple post critical method, we will talk about tension field method. You can see a plate girder that is subjected to a concentrated load, and once the web plates starts to buckle due to shear buckling, it will form a tension band. The tension band will lead to a strut and tie model similar to what is shown below. So the tension band will act like a tension member, and then perpendicular to that will be a compression that is acting. So this will take more load due to the formation of bands, or we also called as folds, and this action is also known as tension field action. The theoretical derivation behind the tension field action will also be discussed in this course. As you can see from the right hand side, how the principal stresses are acting. At one side it is tension, other side it is compression. The derivation will lead to the tension field method that is given in IS 800, as you can see here. Following the design methods for shear buckling, let's talk about elements of a plate girder. The plate girder has several elements: the top flange plates, the bottom flange plates. It also has a web plate. We have an end post, also known as bearing stiffener, as well as transverse stiffener. We also have longitudinal stiffener, as you can see from the isometric view on the left side. Plate girders are very important structural components. It is typically used for long span structures. Long span structures could be basically bridge girders, where you need to have a large amount of moment and shear to be taken care. It can also be used for buildings. Typically the buildings use hot rolled steel sections from IS 808. IS MB 600 basically is the highest load carrying capacity, whose depth is basically 2 feet or 600 mm. Unfortunately, these cross sections cannot be used when the load demand is very high. So you need to go for a plate girder. Plate girder is basically a built up section. You take the plates, cut it and weld it. And this is very common in pre-engineered building industry. The welding is done by what is known as submerged arc welding. So as you can see, the cross section details are given on the right hand side. The depth of the girder is actually given in terms of the depth of the web, and they are connected to the flanges by means of weld, as you can see. We'll also talk about problems, how plate girders can be effectively used to solve or to design bridge structures. So with this one, I would like to say thank you, and I hope you will enjoy the course. I look forward to sharing with you my knowledge in the next semester. Thank you very much.